Yeah, thank you very much for the invitation. Today I will talk about the beauty and the exotica production in heavy ion collision at the LHC. I don't have to motivate more in front of this cloud, and Elena already introduced the physics of heavy quark as a probe of QGP before me. The excitement is that with beauty quark, we are increasing the mass effect, and also beauty quark are more rare and not as well studied as what we have achieved with Chang quark. So therefore, the study of the hadronization, the energy loss of the B quark, and their behavior inside the diffusion inside the quark-gluon plasma is particularly interesting to extend what we have achieved so far with Chang sector. In this talk, I would like to summarize the current status of the experimental study of the beauty hadron. Typically, this is performed with two different ways. The first possibility is to study the non-prime production of Jepside or D-meson or lepton from beauty decay. The pro is that we have higher statistics than the fully reconstructed B hadron. The con, as we know, this provide a partial reconstruction of the B hadron momentum and also they are coming from various of different B hadron decays. And the other direction is to look at into the exclusive B hadron decays. The pro is that we can do a full reconstruction of B hadron momentum and their direction and the flavor. The con is that we will need a lot higher statistics data to achieve such kind of experiment. All right, so with this, I would like to show you a few interesting compilation of current studies. The most precise measurement of beauty suppression is coming from a non-prime gypside, D-meson, and the lepton currently. In particular, at the high PT, the non-prime B to gypside measurement has been very, very precisely performed. In this slide, I compared the result from CNS and Atlas. You can see that the CNS blue points are on top of the Atlas open circle, showing a very nice agreement in mean bias collision. And the other thing which you can observe from this result is that the RA first decrease for the non-prime gypside as a function of PT, and then stay at around 0.4 to 0.5 level at high PT. And also, we can also make a comparison between non-prime gypside RAA, as I mentioned before. They are coming from various of different beauty hadron decays to B plus RAA, and we see that they are pretty much close to each other, although the B plus measurement is not yet as precise as B2 gypside, which can be improved with future data. And of course, there are a lot of interesting measurements also from non-prime D, which is now shown as a yellow open circle from these. And the mu1, which is shown as the open box from Atlas. And you can see that they are pretty much following each other and have a similar general trend as a function of PT. Although, as I mentioned before, they actually carry a different fraction of beauty momentum. So therefore, the horizontal axis is not really the same if we would like to convert that back to the B hadron momentum. And the other thing which we can see in the 0 to 10% measurement is that there are some slight difference between the Atlas and CNS result. As you can see that the green dots are higher than the blue dots, which are the green is actually higher than the red, which are all coming from the B2 gypside measurement. And this possible difference can be coming from the overall normalization for the central event, and it will be interesting to follow this up with round 3 plus round 4 data. So if we take the highest precision Chang and the beauty hadron measurements and put them into a compilation plot, and we see that in this right-hand side figure, we have a comparison between the D-meson and the non-prime gypside measurement. which is non-point dipsization shown as red dots, while the ALICE and CNSD measurements are shown as boxes. And we see a very, very nice agreement between the ALICE D-RAA and the CNS D0-RAA. And it's really nice to see that due to different experimental capability, the low PT reach and high PT reach covered by both experiments give us the most comprehensive understanding of the Chang production. Below 20 GeV, we see that the non-prime zip size is significantly higher than the DRAA. And at high PT, as you can see from here, they start to merge and similar to each other. This is consistent with the expectation from the mass dependence of the parton energy loss, which is an exciting finding from our previous works. On the other hand, the beauty quark heteroanylation data, we don't have a lot of information so far until recently. We have a measurement of BS to B plus ratio presented using 2018 data. And you can see that in the left-hand side, this BS to B plus ratio is measured as a function of number of participants. In the central event, there's an indication of slightly higher BS to B plus ratio in lead-lead condition compared to the blue, which is the PP reference. And if you look at the right-hand side plot, you can see that this is now the presentation of the inclusive BS to B plus ratio as a function of the B meson momentum. And you can see that the result is dropping as a function of momentum and also slightly above the BP reference. And those interesting trends are in line with the expectation from theoretical models, which are shown here. And of course, the accuracy is not yet as precise as we hope and can be improved with the future data. It is interesting to compare the BS to B0 ratio and the BS to and the DS to D0 ratio in PP and heavy ion collisions. The PP data is always shown as the blue in the and you can see that in both PP and lead data, the Chang ratio and the beauty ratios are similar to each other, although the beauty uncertainty is larger. And with a higher statistics data, we will be able to see the possible difference between those ratios in Chang and the beauty sector. Let's move on to the beauty and emission anisotropy. So we have seen significant positive B2 signal reported in the beauty decay lepton measurement. So those are the beautiful measurements from ALICE and the Atlas using beauty lepton. They are significantly deviating from 0, covering a wide BT range. However, the caveat is that the correlation between the lepton and the beauty PT, in particular, the direction is weaker at low PT. And also the lack of structure, the measure of B2 is actually not varying very much as a function of lepton PT. Can be coming from the beauty and emission anisotropy itself, and also the smearing effect I mentioned above. We can also go ahead and compare this data to Upsilon 1s, the hidden BP bar. And you can see that the current picture is that we have an indication of larger V2 from beauty decay lepton compared to Upsilon 1s measurements, which is also shown as the red dots in the boxes here. And also, we can see that we have an indication of smaller beauty V2 signal in high multiplicity PP and proton lead collision. So the blue open squares are from Atlas in PP collision, while the red boxes is actually from high multiplicity proton lead collision. And Japan is going to show some more detail in his talk afterward on the Atlas results. So those are the current status of the beauty studies, and we were thinking about how to actually go beyond the current studies of the heavy Flavour hadrons. And one possibility is that, inspired by this exciting larger RAA in IOGC energy compared to star inclusive gypsum measurement. This shows an indication of recombination effects at low PT. And it would be really interesting to look at this effect with a chunked beauty hadron. That brings me to the discussion of the B sub C measurement. So the physics with B sub C, the B sub C meson is actually below the B plus D mass ratio. If we calculate the delta E with respect to their corresponding ratio for the quarkonia and the B sub C, you arrive this table here. So what we learned from this table is that the binding energy B sub C plus is between gypsum and upsilon 1s. It is sensitive to median-induced dissociation effect, which is interesting. And the other thing is that it has very small production cross-section in PP. So therefore, a slight enhancement will give you a dramatic effect in the changing of the RAA. So it's very sensitive to median-induced effects, such like recombination of beauty with uncorrelated chunk quark. The other thing which is also interesting and unique for the B sub C is that the parton energy loss is an interesting combination of beauty and the chunk quark, and that is adding a richness of the physics with B sub C. So the excitement these days is that for the first time we see a B sub C plus production in heavy ion collision. So the significance is well above 5 sigma now. To keep in mind that the B sub C RAA is presented as a function of visible kinematics. So this means that the PT of the B sub C is partially reconstructed because the channel which we work on is based on the tri-muon channel through this decay chain. So this means that the horizontal axis of the B sub C is plotted by the tri-muon PT. So we see a large experimental uncertainty to be improved with round 3 and round 4 data. At the low PT, if we take the central value seriously, then this means that the central value is actually similar between BS and B sub C. At low PT, the result is higher than all the other species presented here. The charged hadron, which is shown as a red dot, B plus, and the D0 RA. At high PT, you can see that this data point is closer to the other cloud plotted here, and the possibility is that the mass-dependent effects is reducing as a function of PT as we go to high PT. And the interesting picture we see here is that all the different species identified the hadrons seems to converge at high PT at around 20 to 30 GeV in PT. We can, of course, also go ahead and compare the B sub C RAA result to the quarkonia result at CNS, for example. And just a reminder, the binding energy of the B sub C is between gypsum and the boson 1s, which is shown as the purple for the gypsum and the yellow for boson 1s. And you can see that B sub C RAA, the current central value with very large uncertainty, is above all the quarkonia measurements, preventing us from a firm conclusion, which is something interesting to follow up afterward. The recombination effect of the chunk and the beauty could increase the B sub C RAA significantly. And it will be extremely interesting to go to a very low PT below 5 GeV with the future CNS edited setup and these data in round 3 and round 4, hopefully. So if we take a look at this original picture, we can also go in the other direction, which is instead of changing the flavor, we increase the number of balanced quark and see what will happen. Okay, so that brings me to the discussion of the exotica. Of course, the most well-known exotica is the X3A72. This has an interesting signal observed by Bell in 2003 first, but the internal structure of X is still under debate. And the quantum number has been determined to be JPC1++, and that rule out the Chang-Monian interpretation of this state. So the remaining ones are the tetra-quark configuration, which is a compact object with a radius of around 0.3 Fermi, and DD bar molecule can be as large as 5 Fermi, and finally the hybrid of this linear combination of those things or additional contributions from other possible states. So those are all proposed for the description of X state in our data. Instead of taking a passive role by analyzing the decay product of X particle, one possibility is to take an active role to probe the nature of the X particle. So if you compare these two states, as we talked about before, tetra-quark state is compact and small, while the DD bar molecule is loosely bound and large. And of course, one thing we can do is to probe the nature of the X particle with co-moving particles by putting a lot of color charge around those particles and see what will happen. So the left-hand side, you can see that since this state is tightly bound and small, so therefore the co-moving particle effect, of course, will have a smaller dissociation probability for this tetra-quark state, as proposed by this paper, of course. In the right-hand side, you can see that larger dissociation probability could be observed if we have a DD bar molecule state, which is the expectation from this specific model. So the other thing which we can do is to study the production of the X particle in heavy ion collision. Since we have a large volume of deconfined medium, so therefore X particle can be sampled from this interesting medium and see whether the production is actually modified in QGP. So the excitement is that the production rate, for example, in the collections model, is different in tetra-quark scenario versus the molecule scenario, and that will enable us to study and reveal the internal structure of X particle by measuring the production in heavy ion collisions. So what I would like to show you first is the X particle in high multiplicity PP collision from the HCB. So this has been performed as a function of multiplicity in PP collision by the VLO detector. And you can see that they separate the result in prompt and non-prompt from BTK. So for the promptly produced X particle, the X particle is moving with the co-moving particles. So therefore, they can be more easily destroyed by the interaction with other hadrons due to the smaller binding energy. And on the other hand, if we look at the B hadron, which is the decay product of the B hadron, and the X particle is actually produced much later in time. So therefore, the co-moving particle effect is not expected to be significant. And you can see that indeed we see a dramatic different slope between these two type of measurement, which is really intriguing. And we look forward to the future high statistics, high multiplicity data, and the proton ion collision results and see what happens. And the other thing which is input from the teratron data is that the X particle inside in PP bar collision has been measured as a function of the level of their isolation. So the isolation equal to 1 means that this state is fully isolated. On the other hand, 0 means that there are a lot of activity which is around the psi prime or X particle. If we take a ratio of this production rate between X particle and the psi prime, you can see an increasing slope as we go to more and more isolated situation. So this gives although the sigmoid difference is actually not large enough, but this gives us modest support for the hypothesis that the increased hadronic activity at the X particle suppresses its production. So now we arrived this picture here. It is interesting to see what can we actually learn from the collision. So if you follow this trend, this decreasing trend as a function of multiplicity, you will expect no particle producing a collision, no X particles should be producing a collision if the co-moving dissociation is the sole effect. And on the other hand, the coalescence over recombination effect can enhance the X particle production in the collision. And now the question is, what do we see there? So this is the result from the collision at 5 TeV. The results are presented in two ways: the inclusive production, which is shown above, and the B-enriched, which is shown below. And you can see that we see first evidence of X particle production in heavy ion collision with a statistical significance greater than 4 sigma. The fact that there's a X particle peak is already very interesting, actually. And we also see a clear side prime signal decaying to the same final state observing this spectrum. If we go ahead and calculate the ratio of the yield X to side prime, we call it rho, and we see that this ratio of yield is actually very large in central value, but with very large uncertainty currently. The ratio is actually around 1 plus minus 0.5 for the moment. This is the central value is actually much larger than the PP reference at the 7 and 8 TeV measured by CNS and Nautilus. You can see that this is an intriguing result of the enhancement of rho in the collision. And of course, we can go ahead and study how this actually compared to who is actually enhancing this rho. Since we are taking a ratio between X and psi prime, and the psi prime is actually not a very good reference actually in PP collision, in the collision, right? Because psi prime itself is suppressed by a factor of almost like 10. So therefore, you can see that, wow, essentially the RAA of the psi prime is similar to the PP reference. So this means that the take-home message is that if the central value is just staying there, the X particle is actually not modified at all in the collision. So this is something very interesting to follow up. On the other hand, let's take a look at the current status of the theoretical calculation. This is compared by Jing before. So left-hand side is the coalescence model, which I showed you before. The production rate of the molecule will be enhanced with respect to the tetra quark in this model calculation. If you look at the middle part, the NMPT transform model, there's a non-trivial centrality dependence, which is exciting. We see a large enhancement of molecule with respect to tetra quark because of the sampling effect in the large area QGP, which enable us to sample more molecule. If you look at the right-hand side, you can see the TAMU model, transform model. The argument is that the molecule which are loosely bound are regenerated later at a lower density environment. So therefore, the molecule is likely to less enhance compared to tetra quark. The issue is that we still have many different issues taking into account all those interesting measurements in PP and the collision. So what is the role of the multiplicity selection bias? How does that contribute to the suppression pattern? Can we actually increase the accuracy of the current data and the low PT reach? And the consistency between the theoretical calculation, what is the relevance of coalescence tessellation, recombination, model dependence, and absolute branching fractions? So to resolve the first one, we will need to change the source of the co-moving particles using EP, EA, PP, and PA collisions. Accuracy of the current data can be improved with round 3 and round 4 data with new detectors such as a larger substance CNS tracker and round 4, and also the future these 3 detector, for example. We would like to do a stress test with system size scan from EPP, EA, PPPO, and OO collision to the left, which is sampling to the which is sensitive to the sampling fat for the X molecule potassium, and look at the centrality dependence. So therefore, we put all those things into our lab. You can see that although the PT ratios are different, in OHCP is 5 GeV, while the CNS is 15 GeV. You see this intriguing picture. And it will be interesting to follow up all those interesting measurements with future data and the HC via smoke data. So here brings me to the summary of my talk. If we look at the overall picture, the beauty hadron potassium, our understanding is not as good as what we have in the Chang sector. On the other hand, we have observed the mass dependence of the parton energy loss with high precision non-primitive site and the D-meson data, which is exciting. We see an indication of modified beauty hadronization by BS to B plus ratio, but the accuracy is not good enough. It is similar to what that was observed in BS to B0 ratio. And the beauty hadron B2 is observed by heavy flavor lepton, but the details are still lacking, and we still need to understand what will happen if we fully reconstruct the B kinematics. It is interesting to follow up with all those measurements with future high statistics data using fully reconstructed the B and extend those studies with baryons. B sub C plus, exciting new probe, first observed in the Lead collision, larger RAA central value compared to B plus and Quark-Gluon. And we would like to follow this up for sure with other experiment and also going to low PT. And finally, X particle hadron. So first evidence is reported, and the intriguing X to side prime ratio decrease as a function of multiplicity BP. This is a really exciting new probe, and we hope we can extend those to different exotica in the future. And however, the X particle internal structure is still inconclusive due to the experimental accuracy and the model dependence. And there are many interesting issues to follow up with future data, and please stay tuned with all those interesting developments. So that's all I want to talk about. Thank you very much.
Thank you. Thanks for this very nice and informative talk. We have time for some questions, either here or from outside. First in the room, no immediate questions. It seems to me that Ralph has his hand, so please.
Yeah, hi, Yen-Jie, very nice talk. I wanted to reiterate the importance of measuring the absolute yields of the BC and the X in PP collisions, because if you plot an RAA, the recombination yield will depend very much on the denominator, because the numerator is independent of the denominator, right? So, yeah, right. In particular also for the BC, we have some calculations, but the results really strongly depend on what you put in the denominator for the PP cross-section. Also for the X, there's still an issue with the branching ratios, I think. Can you comment on the future perspectives of nailing down the PP cross-sections?
Yes, I think we for sure can perform such a measurement with the PP cross-section. Yeah, so yeah, I think yeah, so that's actually in the for sure in the work, and hopefully we can with a future higher statistics data, we should be able to achieve those. Yeah, I understand the importance.
Okay, thanks. The alternative would be get an absolute measure cross section in lead, of course.
Yes, of course. That's actually also I don't see anything preventing us from doing that. Yeah. Thank you for the comment.
Okay, so the room is still silent. So Francesco.
Yes, hello, Yen-Jie. So it's a curiosity not only on what was the focus on your talk, but you showed in slide 5, if I remember well, that there is a small tension between the non-prompt psi RAA of Anderson CMS for central events. And if I didn't understood wrongly, you mentioned that it could be an issue with the normalization. Yeah. If I remember correctly, for the prompt psi, the agreement is okay. So this somehow questions the point of normalization. And I was wondering in slide 6, I missed which of the two you have shown to compare to these and to make the point on the larger area, because this might have an impact on what we conclude on the D versus B area.
Yes, yeah, so thank you for the comment. So I think currently the issue is that when we go to 0 to 10%, then you have this TAA calculation and the associated uncertainty for selecting the most central event, and that could play some role. And of course, other experimental effects such as the tracking and muon reconstruction effect in central event can also come into play. So in an inclusive case, the modulation seems to be pretty straightforward, and we do see a quite good agreement. But keep in mind that after state measurement is actually from 0 to 80%. So that could be some very slight difference, but I don't expect to be a very large effect. But you can see that here the difference is around like a 0.05 in RA. So the taken data is from CNS. So if you move, even if you move this by 0.05, and the conclusive still holds in slide number 6. So and on the other hand, the non-presumptive side data should be moved toward the right-hand side slightly by something like 2 GeV to get back to B Meisang RA. That will further enhance the difference between the RA measured by B and the D Meisang. So that's all in the right direction. I don't know if that answers your question.
Yeah, okay, thank you.
Okay, good. Other questions here or outside? Francesco has just asked his question. And yeah, so this is not the case. So still thanks, Yen-Jie.